All right, so for the geometric series where we know the first term is a sub 1 and each term is found by 3 times the previous, you could see we would have -6, then -18, and then times another 3 would give us negative, what's that going to be? 54, then negative 162, etc. So you see the first term is -6, that's a, or a sub 1, and our ratio is 3. So the way you find the nth term is ar to the n minus 1. So in this case it would be -6 times 3 to the n minus 1. All right, here if we're going to solve this, we want to isolate the exponential function, so we got to divide by the 7 first. So you have 10 to the x minus 3 equals 23 over 7. Then we need to get rid of this base 10, so we're going to do log base 10 on either side. That allows us to cancel this 10 as the exponential. Now we have x minus 3 equals log of 23 over 7. Add the 3 to the other side, and you've figured out what x equals. And if you wanted to get an estimate of what that really was, you could plug that in your calculator and you would get about 3.517. But this is the exact answer. Okay, here we're going to find the real zeros. So first we want to set this equal to 0, the function, and solve the resulting equation. So being a polynomial equation, we're going to try and factor this. You have different ways you can factor, either using, factoring by hand or do synthetic division. In this case, it's pretty easy to factor by hand. I'll pull out an x squared. I'm left with x squared plus 7x plus 6. That could factor even more as x squared times x plus 6 times x plus 1. So you see each factor is going to give you your 0. This is going to give me the 0, x equals 0. This is going to give me the 0, x equals -6. And this will give me the 0, x equals -1. Now as far as the multiplicity goes, it's the amount of times the 0 is repeated. So it's also based off of the power that the factor that gave you that 0 was raised to. In this case, this factor x gave me this 0, but it was raised to the second power, so that has multiplicity of 2. This one has a multiplicity of 1, and this one has a multiplicity of 1. All right, if we want to figure out what quadrant -70 degrees is in, if we're going negative, we would have to go this direction. We'd have to go clockwise. If we go a quarter turn, we get to 90. So there's -90 degrees. So -70 would have to be in here. And that would tell us we're in quadrant 4. All right, so we want to write the equation of the line that's through the given point. That's -2, 0, and parallel to this line here. So we would have to find the slope of this line. So this is in this ax plus by equals c format, standard form. And when we have it in standard form, the slope is always going to be -a over b. So in that case, we're going to get -24 over 8, which gives us +3. So there's your slope. Now the parallel slope should be exactly the same as that. If it said perpendicular slope, then it would be negative reciprocal, but that's not what we wanted here. We wanted parallel, so it's the same. And we have this point here, so now we can use the point slope formula, y minus y1 equals m times x minus x1. And we would get y minus 0 equals 3 times x minus -2. So y equals 3x plus 6 would be the slope-intercept form of the line we were looking for. We need the formula for an ellipse to do this problem, which would be our x minus h squared over a squared plus y minus k squared over b squared equals 1. HK being the center and the A and B helping us to find the different points around the ellipse. Now in order to get there, we need to use completing the square. So we're going to rewrite this as 4x squared minus 40x plus 16y squared plus 192y equals negative 612, just moving some terms around. I got to factor out a 4 and a 16 out of each one of these. So I'm going to have 4 times x squared minus 10x. And here I'm going to have 16 factored out, and I get y squared plus 192 divided by 16 would give me 12y. And here I just still have the negative 1, the 612. So now it's time to complete the square. Everything's set up to go. So we'll divide negative 10 by 2, and we're going to get 5, and we're going to square that. And we'll take 12 divided by 2, and we'll get 6, and we're going to square that. So that allows me to take this and factor it as x minus 5 squared, and this would be y plus 6 squared. I still have the 4 and the 16. But now what I have to do is I have to alter the other side of the equation because I added these pieces in. So here I have 4 times this and 16 times this. So 4 times 25 would give me an extra 100. And 16 times 36 would give me an extra 576. So I have to add those pieces to the other side. So now the other side would be 576 plus 100 minus 612, which would give me 64. Then I'm going to have to make this a 1 to match up with the formula, so I'll divide by 64, and that would give me all these divided by 64. So that would give me x minus 5 squared over 64 divided by 4 is 16 plus y plus 6 squared over 16 divided by 64 is 4, and then this would be a 1. So now we have everything we need. So we have the center to be 5, negative 6. Now if you remember how you find your vertices are based off of knowing whether you have a vertical or horizontal ellipse. Since this square is bigger than this square, we're going to have a horizontal ellipse. So we have the center here, and then these 2 points here are our vertices. So we have to figure out how far away from the center we would go, but it would be basically traveling horizontally. So we'd be changing the x value. And it's based off of this. So A will tell us how far we go. In this case, A, if that's A squared, A is 4. So if we go 4 units and 4 units away from this point 5, negative 6, that would give us our vertices to be 1, negative 6, and 9, negative 6. Okay, here we need to know the formula to find the nth term of an arithmetic sequence, and so that formula would be that a sub n equals a plus n minus 1 times d. In this case we have a sub 1 and we have d, so it's pretty simple. A sub n equals negative 3 plus n minus 1 times negative 7. Do a little computation here, negative 3. This will be minus 7n plus 7, and so we get negative 7n plus 4. So that would be your formula to generate your a sub nth term for the arithmetic sequence. So here we want to talk about a rational function. First, look at its domain. Okay, domain is all about the denominator not being equal to 0. So if we set it equal to 0 and solve, you can quickly see that you're going to get negative 5x equals negative 6, x equals 6/5. So that's exactly the x value you don't want. So we can say the domain is all x except x equals 6/5. Okay. Then we want to talk about horizontal and vertical asymptotes. Let's do horizontal first. Horizontal asymptotes are all about the degree. The degree of the numerator is 1, the degree of the denominator is 1. So since the degrees are the same, we take the leading coefficients and divide them. So our horizontal asymptote will simply be y equals 2/5. It's negative 2 over negative 5, but the negatives would cancel. So y equals 2/5 is the horizontal asymptote. It's y equals, not just 2/5, but it's a line, so we write y equals 2/5. Vertical asymptote goes back to the idea of domain, and it's about what happens when the denominator is 0. In this case, since it's simplified as much as possible, only looking at when the denominator is 0 would be good enough. Sometimes we have to worry about the numerator being 0 as well, in which case we would get a whole, but that's not happening here. So our vertical asymptote would simply be x equals 6/5. Here we want to identify the vertical asymptote for this function. That's probably best done by looking at translations. So we think about a logarithm. This is a log base 10, so generally the logarithm base 10 would have this shape to it. It would go through this point 1, 0 and have a vertical asymptote that is the y-axis. Now this one is moved a little bit. Here we have a +3 and then here's a +2. So this is going to move it to the left 2 units and this is going to move it up 2 units. So if we take this vertical asymptote and we have to move it left 3 units and up 2 units, it's going to be sitting right here is now the vertical asymptote, and my graph would go appropriately like that. But the vertical asymptote would be here at -3. So x equals -3 would be my vertical asymptote. So this example, unlike the 2 previous, we do have to simplify this function to talk about the vertical asymptotes. But domain, we really look at this before we simplify. So I will factor it though. I will look at this as x plus 6, x minus 6 over 7x minus 5 times x plus 6. And so domain is all about the denominator not being 0. And seeing it in factored form, we would see this would be 0 when x equals 5/7, and this would be 0 when x equals -6. So those are the things we don't want. So the domain is all x except x equals 5/7 and x equals -6. Okay? 6. Now horizontal asymptote, we do that and vertical asymptote based off of the simplified version of this. So if we cancel these x plus 6, we get x minus 6 over 7x minus 5. Horizontal asymptote is about degree. The degree of both of these is 1, so we'd use the leading coefficients 1 and 7. So our horizontal asymptote would be y equals 1/7. And then our vertical asymptote is all about the denominator in the simplified form being 0. We canceled this one out, which is where we would have a whole but not a vertical asymptote. So our vertical asymptote is only going to be where this factor is 0, which would be when x equals 5/7. So there's your vertical asymptote. So here we want to talk about how we're going to transform this function into this function graphically. And looking at the differences to +3 up in the exponent, which is the inside of the function. Whenever you add 3 inside the function, you shift the graph left 3 units. So we would say the operation would be shift the graph left 3 units. Okay, we want to evaluate the sign of -2 pi thirds. If you look at where -2 pi thirds would fall, it would fall in quadrant 3. That's where -2 pi thirds would end up that angle measure would fall. So if we're in quadrant 3, we should understand that the sine is based off of the y coordinate and would be negative. And so then we just need to figure out what the value of the y coordinate is. Well, that would be the same as looking at what the sine of pi thirds is. And so if you remember what the sine of pi thirds is, when you use your unit circle, pi thirds would be this one right here. So we would figure out what the y coordinate is. And if we want to know what the y coordinate is there, that would be my square root of 3 over 2. So this would be negative square root of 3 over 2 as the value for the negative sine of negative 2 pi thirds. Okay, here we want to find the exact value. One way we're going to do that is by rewriting it. So I'm going to write this as the cube root of 7 squared, which is 49, which I can then write as log base 7 of 7 to the 2/3, writing the exponent, the root as a fractional exponent. And then the idea of how we do this is what the log's asking us to do is saying 7 to what power gives us this. Well, 7 to the 2/3 power would give us that. So the exponent that we were looking for here is 2/3. And that's the exact value. Okay, so we want to solve this equation. The nice thing is we were giving one root of the equation already, so we know how to start it. So it's basically telling us that x plus 1 is a factor, and we need the other factors of this polynomial to finish solving the equation. So if we use synthetic division, negative 1 is a root, so we'll put it on the outside. We have 1, 2, negative 1, negative 2. We'll bring down the first 1, multiply. We get negative 1, we'll add. Then we'll multiply again, and we'll get negative 1, and we'll add. Then we'll multiply again, and we'll get 2, and we'll add. And we knew we were going to get a remainder of 0. But this is what we were looking for, the other factor, which will give us x squared plus x minus 2. So now what we have to do is factor this a little bit further if possible. So what do we have? We have x plus 1 times x plus 2 minus 1. So our zeros, or our solutions, would be x equals negative 1, x equals negative 2, and x equals positive 1. Okay, we want to determine whether or not this is a geometric sequence, and typically the way we would do that is if there's something we can multiply to get from one term to the next to the next. So we can do that by dividing two consecutive terms and always getting the same thing. So negative 8 divided by negative 5 should be equal to negative 11 divided by negative 8 should be equal to negative 14 divided by negative 11. And the problem with this is that they are not equal to each other. These are not equal, these are not equal. So since there isn't a single thing that I was multiplying to get from term to term to term, then this is not a geometric sequence. Okay, here we need a couple of things. One, you need to recognize that the center is based off of 8, 7. And you also have to recognize that this is a vertically oriented hyperbola. So the foci would be oriented vertically off of this center. We just need to figure out how far, and that's based off of C. So we need to know what A and B are. So in this case, A is going to be your bigger value, and that would give me 7. And B would be the square root of 32, which would give me 4 times the square root of 2 if you wanted to simplify it, because this is 16 times 2. And so C is always equal to the square root of A squared plus B squared. And so C would be the square root of 49 plus 32. and that would give me the square root of 81. So that's going to give me 9. So I have to go 9 units vertically off the center. So that would be adding and subtracting to the y value. So the foci would be at 8, -2, and 8, 16. Okay, here we want to use synthetic division to divide this. Well, one thing you got to remember is that we're missing a square in here. So we have 1, 0, -12, 16, 0 for the missing square. We're going to put a positive 2 out here, bring the 1 down, multiply, add, multiply, add, multiply, add. So if we were to do the division, we would say that x cubed minus 12x plus 16 divided by x minus 2 equals x squared plus 2x minus 8, and there's no remainder, so we don't have to worry about that. To find the sign of minus pi fourths, you got to realize that minus pi fourths falls right here in quadrant 4. This would be minus pi fourths. You should know that the sign of positive pi fourths is going to have a y coordinate square root of 2 over 2, so that's going to be the sign. So this would give me the negative square root of 2 over 2 for sign of negative pi fourths. There are two ways we can do the summation. One is just plug 1, 2, 3, 4, 5 in for I, and then add those up, which isn't bad because there's only 5 terms, but if there was, say, 100 terms, that would be very time consuming. So what we're going to use instead is these two formulas, the sum of I equals 1 to n of I, and the sum of I equals 1 to n of a constant. In which case this one is going to be n times n plus 1 over 2, and this one's going to be constant times n. So we're going to use some properties here. We're going to say we can split this apart into the sum of I equals 1 to 5 of negative 2i plus the sum of I equals 1 to 5 of 3. Then we can pull this negative 2 out as a constant multiple. And now we have the sum of I and the sum of a constant using these two formulas, where n is 5 in either case. We get negative 2 times 5 plus 6 over 2 plus 3 times 5. You do that computation, you see you get negative 15. So here we need to solve this polynomial inequality. And when we solve these, the first thing we need to do is we need to make sure that one side is 0, so we're less than or greater than 0. In this case, we're looking for this polynomial to be less than 0. So then what we're going to do is we're going to solve what happens when it's equal to 0. In which case we would get this factored as x minus 3, x plus 2. And we would get x equals 3 and x equals negative 2. Those are the zeros of the polynomial. That's when it's equal to 0. But we don't want to know when it's equal to 0. We want to know when it's less than 0. So then the next thing we're going to do is we're going to set up this number line. We're going to place negative 2 and 3 on this number line. And we're going to look at this polynomial x squared minus x minus 6, and we're going to try to figure out when is it negative. Well, these are the two places where it's equal to 0. So everywhere else, it's either going to be positive or negative. So we're going to look at this interval, and this interval. We can choose a value from this interval here. Let's say, I don't know, negative 3. One from here, say 0, and one from over here, say 4. And we can plug them into the function to see what's happening. You also know that this is a parabola, a positive parabola, because the positive x squared. So it's going to look like this. In which case, basically where it's equal to 0 are the x-intercepts, so the zeros, so negative 2 and 3. So based off of this picture here that it's a positive parabola, it's negative or below the x-axis here, and positive or above the x-axis here and here. So we should get plus, minus, plus here with our chart. But also if I just plug negative 3 into that thing, you should see you're going to get 9 minus negative 3 minus 6, which is going to give me 9 plus 3 minus 6. and therefore I'm going to get 12 minus 6, which is 6, which is a positive value. So either by plugging this in, we could see we're going to get a positive, a negative, and a positive, or by looking at the graph. But ultimately what we want to know is the solution to the inequality. So we're looking for when is this polynomial less than 0, which would be negative, which would be here. So the solution would be on the interval -2 to 3. And I'm putting parentheses around the -2 and 3 because we don't have the or equal to 0. This is where it's equal to 0. We don't want that. We just want negative, less than 0. All right, here we're going to solve this equation for x. In order to do that, we need to put these two logs together first using our log property. So that would be the log of x squared times 5, or sorry, divided by 5, the division because of the subtraction there, and that equals 0. Now what we want to do is get rid of the logarithm. Since we have a single logarithm by itself, we'll exponentiate both sides, use base e. E is the inverse of the logarithm. So that's why we're going to use e, but we have to do it on both sides. That allows these to cancel, giving me x squared over 5 equals e to the 0. E to the 0 is 1. Multiply 5 to the other side, I get x squared equals 5. So x equals plus and minus the square root of 5. Now we want to double check to make sure that those two solutions, square root of 5 and negative square root of 5, would work. Well, if I plug negative or positive square root of 5 in here for x squared, I'd be squaring it, and therefore I would get, in either case, 5, so it would give me log of 5 minus log of 5 equals 0, which makes sense. That does equal 0. So both of these are going to be your solution. So here we want to describe the behavior at the endpoints for the graph. That's all based off the leading coefficient test, and it's based off of this term. I have a negative coefficient, and I have an even power. So right there, that tells me I'm going to have down on both ends of the graph. So I could say, as x approaches negative infinity, y would approach negative infinity. That's what's happening on the left side. And as x is approaching positive infinity, y is approaching negative infinity. That's what's happening on the other side. And it's all based off of the leading coefficient test and looking at the power being even or odd and the coefficient being positive or negative. Here we want to expand this expression. So we have a logarithm with a quotient inside of it. So division turns into subtraction when it comes to logarithms. And we also have a power here. Powers can come out to the front as a constant multiple. So that would be the full expansion of this logarithm. We can't really go any further here. There's not much more I can break up in these logs. So there's my answer. So here we want to find the vertex and focus of the parabola. Since x is being squared, we want to write it in the form of x squared equals 4py. In which case, if we did that, we would say x squared equals 28y, or x squared equals 4 times 7 times y, in this case p being 7. Now the reason for the p there is to find the focus. So when we have this set up, the vertex is always going to be 0, 0, but the focus would be 0p. So in this case, that would give us 0, 7. So vertex at 0, 0, focus at 0, 7. It's a positive square parabola, so that would open us up along the y-axis like this. Here would be your focus right in the middle there at 0, 7, and your vertex would be here at 0, 0. So we need to determine whether or not this is an arithmetic sequence, and that's all based off of if you're adding something to get to each term, and that's going to be the same value every time. Well, clearly you can see that I add 1, then I add 1, then I add 1, then I add 1. You could also check to see if you subtracted any two consecutive terms. You get the same thing every single time. If that's the case, you do have an arithmetic sequence. So yes, this is arithmetic. And the common difference is 1.